quite a classic problem here. So we'll start off with a diagram, and you'll see I've just shown how the ball will fall. It's going to hit the ground, and of course it'll bounce back up again. Because the initial direction of motion is downwards, I've chosen downwards to be positive. We can see we can simply use a Suvat equation to find the final velocity, i.e. the velocity when the ground was struck. So v squared is u squared plus 2as. Substitute in the values and you should see that v will equal the positive square root of root 2gh. Now for questions like this, I actually find it slightly easier to work with speeds because there's going to be changing directions throughout. So what I'm going to say is that the speed after the bounce will equal e times by the speed before, and so in this particular case it'll be e times by root 2gh. Now I'm going to consider that first bounce upwards. So we have an initial velocity of e root 2gh. My velocity at the highest point will be 0. I've taken upwards as positive this time. I'm trying to find out how high it bounces, so I'm going to find s. And my acceleration, of course, will be minus g. So again, I'm going to use v squared equals u squared plus 2as. Substitute in the values, as you can see here, making sure you've got the acceleration as a negative. Rearrangement, and then dividing throughout by 2g leaves me with the height that it bounces to is e squared h. Now at this point in time you could simply repeat the process for the next phase of the motion and subsequent phases until you can see a pattern. However, a little bit more thought will show you that the first height attained was e squared times by the previous height, and so naturally for the next bounce it'll be e squared times by this height, which would be e to the 4h, and for the next bounce after that e squared times by that height, so e squared times e to the 4h, which would be e to the 6h. So I'll just say here we could repeat the process, but just a little bit of thought will show you that we can answer this in a much easier way by noticing that for each subsequent bounce e squared times by the previous height is all that we need. So if we do a diagram now showing some subsequent bounces, it will look like this. You'll notice I've shown downward motion in green and upward motion in red. When we're looking for the total distance travelled, we're going to have to think about both of these parts or aspects of the journey. There are two ways we could go about this. We could put an extra red arrow by the first green arrow and then remember to subtract a h at the end of the process. However, what I'm going to say is that the downward distances plus the upward distances will look something like this. And what we should notice is that these are both geometric series with a common ratio of e squared. And furthermore, because e itself is less than or equal to 1, and in this case I think it only makes sense that e is strictly less than 1, of course, there'll be a sum to infinity. So a quick reminder, our formula for a sum to infinity is a over 1 minus r, and so I can sum together each of the two different aspects of the motion, and then I can simply pull a factor of h out and say the total distance travelled will be h parenthesis 1 plus e squared over parenthesis 1 minus e squared, and that's the problem finished. Of course, this kind of works on the presumption that it will bounce on and on forever, but in our theoretical model, that's precisely what it will do. Review the question carefully. Make sure you understand this problem. It's not one to learn, it's one to think about, appreciate, and then be able to go through the process yourselves.